Okay, continuing where we left off with lesson 8.8, we were right in the middle, or right near the end, I should say, of finishing up the integral from negative infinity to positive infinity of 1 over 1 plus x squared. We set up two limits after we broke the integral up, integrating from negative infinity to 0. An antiderivative, I hope we are going to remember quickly, would be the inverse tangent of x. And like I had said earlier, really we only need to look at one of these integrals at a time. We should very quickly finish up the fundamental theorem and just see if this integral will exist, especially when we apply the limit. Well, we know the inverse tangent of 0 is 0. But you might wonder what the inverse tangent of negative infinity is using this limit. Well, the graph of inverse tangent, doing this quickly, is going to look like what I'm jotting down right here. So we're going to know that as we approach negative infinity, inverse tangent is going to approach negative pi over 2. So this will be 0 minus negative pi over 2. In other words, this whole integral is going to arrive at pi over 2. Now, we're going to do the same thing over here, and we're going to say, well, the antiderivative, very much like we did a moment ago, is going to arrive at inverse tangent. And this time we'll apply the fundamental theorem from w to 0. And as we do that, we're going to have the inverse tangent of w minus the inverse tangent of 0. Again, the inverse tangent of 0 is 0, but look back at this graph. You can see as w is approaching infinity, tangent itself, inverse tangent I should say, is approaching pi over 2. So this is going to be pi over 2 minus 0. And really what we have right now, just adding these two limit components together, we'd have a pi over 2 for our first integral, pi over 2 for our second integral. Believe it or not, this entire integral, the original problem, converges, and it converges to pi. Okay, continuing on, very often we will encounter functions that have an infinite discontinuity at one of the endpoints, over a finite interval, that is. Look at one of these endpoints. Maybe there's an infinite discontinuity at b, the right endpoint. Well, we still have to set up a limit where t is going to approach b, but only from one side, in this case from the left. What if our infinite discontinuity would be, say, at the left endpoint? Well, in that regard, we're still going to have to set up a limit. And in that regard, we're going to have t approaching a from the right. And then we'll proceed just as we have before. Well, let's go ahead and see if we could quickly come up with a problem here. I think as we look at number 4, it's pretty clear that we're in trouble when x equals 2. F of 2 would not be continuous. It wouldn't exist. And inside the integrand, of course. So what I'm going to do is set up the limit as t approaches 2 from the right. And then we're going to look at this problem as the integral from t to 5 of 1 over radical x minus 2 dx. It's very tempting at this point to want to use a u substitution. However, just think about it this way. If you just had 1 over radical x inside of the integrand, that could be written as x to the negative 1/2. And in that regard, you would take the power rule, reversing the power rule for an antiderivative, adding 1 to your power and dividing by that new power. If we add a 1 to negative 1/2, we'd get positive 1/2. And then dividing by a half, we'd get 2. Now look, this is a wonderful shortcut to working this out without requiring us to use a u substitution. We can just do the same thing, even though in this problem we have 1 over radical x minus 2. We can say, well, this is like x minus 2 to the negative 1/2 power. We'd add a 1 to that exponent and divide by that new power, and thank goodness we get a nice antiderivative. If you're ever worried that you have not, take a quick derivative to check. Finish this up with the fundamental theorem, and we can see quickly this becomes 2 times the square root of 5 minus 2 minus 2 times the square root of t minus 2. Now, of course, 5 minus 2 is 3, so this would become 2 radical 3. And remember, 2 is only being approached from the right. We're going to only have t approaching 2 being a little bit larger than 2, like 2.001. That's very, very pertinent in this problem, because for this limit to exist, that argument, the inside of that radical, must remain positive. So you can see what's going to happen. And of course, you could be approaching 0 as well. But this is going to arrive at 0. This integral converges to 2 root 3. As we're looking at number 5, I hope you know and you remember that the secant of pi over 2 is undefined. That's because the cosine of pi over 2 is 0, and the reciprocal of 0, of course, is undefined. So again, let's set up a limit, and this time we could say let's let t approach pi over 2. This time we're going to approach from the left side. And you might remember just the other day that we did in fact ask students to memorize the antiderivative of secant, and for good reason. It shows up enough. The antiderivative of secant was the natural log of the absolute value of secant x plus tangent of x. And from here we're going to use our fundamental theorem from t to 0. Well, if we were to very quickly investigate what's happening, we could say, well, we've got the natural log of the secant of t plus the tangent of t minus the natural log of the secant of 0 plus the tangent of 0. Now, of course, secant of 0 is 1, tangent of 0 is 0, and the natural log of 1 is 0 itself. So this second component here actually won't exist. But as we're looking at the secant plus the tangent, I think here we're going to have to give this a little bit of thought. As we're investigating the natural log of secant plus tangent, it's helpful to look at their graphs. The secant graph, just sketching that very quickly, around pi over 2, you can see that you're approaching positive infinity. Similarly for tangent, as you approach pi over 2 from the left, you'd be approaching positive infinity. Now, infinity plus infinity, there's no conflict here. You're just going to get an even larger size of infinity, so to speak. And the natural log of infinity itself is infinity. So this is infinity for this natural log component. The second part was the natural log of 1. That actually just collapses down to 0. So this integral would be approaching infinity. We would say that it diverges. So finishing off, we've got one more problem, and this is by far the trickiest problem where students can really get into some trouble. Uh, please be careful with number 6. Let's read this definition. If f has an infinite discontinuity somewhere in between the endpoints, c in some open interval, some number of x between the left and the right endpoints, it's continuous elsewhere, then what you need to do is break this up into two different integrals, and provided that both of the improper integrals converge, then the original problem will converge. If either one of those two integrals diverges, the original problem diverges. Why is this so tricky? Well, we're never going to look at an integral the same way, honestly. You can see that f of 1 is undefined. You'd have a discontinuity at x equals 1. So that means we have to write this problem out. We're going to integrate from 0 to 1 of dx over x minus 1 plus the integral from 1 to 3 of dx over x minus 1. And of course we need limits. We're going to let t approach 1. This time from the left, we can only be approaching 1 getting a little bit smaller than it, like at 0.9 on that endpoint. And we're going to, of course, integrate between 0 and t of our dx over x minus 1. From here, I'm going to say we need another limit. Maybe we could have w or some other letter approach 1, this time from the right, just being a little bit larger than 1. And we'll have w down below, up here is 3. And just as we've talked about earlier, a quick way to find an antiderivative is to say we've got the natural log of the absolute value of x minus 1. Notice that here we really would like to have absolute values. And we're going to have our limit out in front. Then over this way, we'll have our other integral. Now, maybe you'd like to just pause on that for a moment, because let's see what's about to happen. As I apply the fundamental theorem, I'd get the natural log of t minus 1 minus the natural log of 0 minus 1. And don't forget, this is still a limit. The limit is t is approaching 1 from the left. Now, as t approaches 1 from the left, obviously, we're focused in right here on this first part of the fundamental theorem. Natural log of t minus 1, very often kids just want to plug in the 1 itself, and they'll say, oh, that's the natural log of 0. But look, if you're plugging in something that has 1 approached from the left, you might be plugging in something like 0.99999. Now, once you plug in 0.99999, you subtract a 1, you get something very tiny. Take the absolute value of it. It's a positive tiny value. Up here, I'm going to redraw a graph of the natural log function. It would look something like this. As you have a very tiny x value plugged in, this is going towards negative infinity. And of course, the second part of this is just going to be the natural log of 1, which is 0. Right now, we can say that this problem diverges. I don't even need to check the second integral. I don't even need to work that out. You must have both of the improper integrals converging if your original problem is to converge. It's not, so we can say without worry that this problem diverges. There is a very, very, very big danger. Sometimes people forget that there is a discontinuity. I'm going to say watch out. So very often kids might quickly look at a problem like this and say, what's so difficult? I'm just going to use the fundamental theorem. Here's natural log of absolute value of x minus 1. Plug in a 3. we get 3 minus 1 minus the natural log of 0 minus